Hey guys, today I will present a generalization to a viewer suggestion. We were asked to determine the number of subsets of 1, 2, up to 5n with sum divisible by 5. This is a nice introductory problem for roots of unity filtering, so we wanted to present such a solution. But since there also exists another easy solution with induction to that problem, we decided to generalize it. Namely, we want to determine the number of L-element subsets of 1, 2, up to 5n with sum divisible by 5. The proof with roots of unity filters is almost the same, but an inductive solution is harder. You can try to find such a solution on your own as a small exercise. To solve this problem, we want to use generating functions. Namely, we define a sequence aij such that aij is the number of j-element subsets with sum I. We are interested in determining the number nj, which is now equal to the sum over all I divisible by 5 of aij. We define the polynomial p of x, y in such a way that it is equal to the sum of all possible values of I and j. And here I is going from 0 to 5n plus 1 over 2, and j going from 0 to 5n of aij times x to the power of I, y to the power of j. This is an example of a generating function where the coefficient in front of xi is some bi for some sequence, or here we have two indices, so the coefficient of xi times y to the power of j is exactly aij. And since aij is 0 for I or j large, we are here dealing with just a polynomial. We can rewrite this object due to our definition of aij, and namely this is the product of k going from 1 to 5n of 1 plus x to the power of k times y. To see why this equality is true, we interpret this product. Namely, we can go through each of those terms, and every time we can choose either the 1 or x to the power of k times y. And here this corresponds to choosing this k in our subset, and then we're going to obtain an exponent of plus k for the x, which increases our I by k, and we multiply by y, which is also good because y to the power of j corresponds to a j-element subset. Recall that we want to evaluate the sum of aij for I divisible by 5 and some fixed j. And now we remember a useful formula that we previously discussed in another video, and we uploaded a solution to this in a YouTube short that you can find here. And this identity is that 1/5 times the sum of k going from 1 to 5 of omega 5, and this is the fifth root of unity, to the power of k times I is equal to 1 for I divisible by 5 and 0 otherwise. This tells us that if we plug in omega 5 for x in p and omega 5 squared also, and all those up to omega 5 to the power of 5, and sum all of these values up and then divide by 5, all of the terms where I is not divisible by 5 are going to vanish, whereas the other ones will remain. So let's do this. We get that 1/5 times the sum of k going from 1 to 5 of p of omega 5 to the power of k and y is equal, and now I'm going to sum first over the values for j, so equal to the sum of j going from 0 to 5n, and now only the values of I where 5 divides I of aij times y to the power of j. Notice that this term right here is exactly equal to nj, so what we obtain here is the sum of all those values for j of nj times y to the power of j. So now we want to evaluate this polynomial to get our nj's, so what is left to do for us is to evaluate p of omega 5 to the power of k, y. If we plug this in for k is equal to 5, we just get p of 1 comma y, and this should be really easy to evaluate using this product formula. And indeed, p of 1 comma y is the product of k going from 1 to 5n of 1 plus y. Or in other words, this is 1 plus y to the power of 5n. Now we take a look at the other case, and I'm going to rename this exponent with r because we already used k here. So we want to consider r is not equal to 5, or more generally, 5 does not divide r. And then we obtain that p of omega 5 to the power of r comma y is equal to that product where we plug in the value for x. But here we see that if we replace k with k plus 5, we get the exact same value because omega 5 to the power of r is the fifth root of unity. And so we can also write this as the product of k going from 1 to 5 of 1 plus omega 5 to the power of r times k times y, all to the power of n. To evaluate this, we remember that we saw in our introduction to complex numbers that x to the power of 5 minus 1 is equal to the product of k going from 1 to 5 of x minus omega 5 to the power of k. And this looks really similar to that product. To get into this exact form, we factor out negative y to the power of 5, because then we are left here with the product of k going from 1 to 5 of negative y to the power of minus 1 minus just omega 5 to the power of rk. And we take all of this again to the power of n. Now we notice that we chose r such that it is not divisible by 5. Therefore, the residue classes r, 2r, 3r, 4r, and 5r are exactly just residue classes 1, 2, 3, 4, 5 modulo 5. Therefore, we can remove the r right here. And then we are exactly in this form here with x equals to minus y to the power of negative 1. And so we get negative y to the power of 5 times negative y to the power of minus 1 to the power of 5 minus 1, all to the power of n. And this right here is just plus 1 plus y to the power of 5, all to the power of n. We use these informations to now get our final form for the sum over all j of nj y to the power of j. Namely, this is equal to 1 plus y to the power of 5n plus 1 plus y to the power of 5 to the power of n times 4, because we have 4 possible values for r here. So plus 4 times 1 plus y to the power of 5 to the power of n. And finally, we divide by 5. Therefore, we get for our final answer as nj the coefficient in front of y to the power of j here. And thus, nj is equal to 1/5 times 5n over j. If j is not divisible by 5, then that's it. So this is for 5 does not divide j. And otherwise, we get the same first summand. And moreover, we get 4 times divided by 5, 4/5, times n over j divided by 5. And this is our final answer, and therefore we are done.